Good morning, sir.
Good morning. All right, so good morning, everybody. Anybody have any questions before we continue?
How's your day going, sir?
Good, not bad. How are you guys? How are you doing?
Today's a great day.
I heard there was a quarantine in one of the companies.
Yes, sir. Second
which-
co.
Second company. How many students is that? How many midshipmen?
Yeah, that's my company, sir.
How many people is that?
I believe we have 7 PUIs right now, but in total, it's a good amount. There's like 80 of us in the company.
So for 2 weeks, you can't leave your rooms?
We're allowed to actually go get our dinner and stuff, but for the most part, we have to be in our rooms. The PUIs can't leave though.
Okay. All right. Well, we won't have any exams for a few more weeks, so hopefully it'll clear up by then. All right. Well, good luck for the quarantine. Any differential equations questions? Any questions about the course at all? Homework? Web assign? Okay. So last time we did this IRA problem, savings account problem, and we saw this was the differential equation. Initial conditions, interest rate 8%. Every year we deposited $2,000. And we solved the differential equation using the integrating factor method for linear first order differential equation. And then we solved the problem. We figured out how much money we'd have after 40 years in our bank account. So this problem is similar. So I'd like you to give it a try. So a mortgage starts at $100,000. The interest rate is 7%. And we pay $8,000 a year continuously, compounded, and interest is compounded continuously, just like this problem. Try to set up a differential equation like this. It'll be similar. That would allow you to figure out the balance as a function of time. So we would like to know S of t, which would be our balance at time t. All right, so the next person up looks like Mr. Ko. So I'll give you a minute to see if you can come up with the differential equation, and then we could try to quickly solve it.
Sir, what was the rate?
The rate is 7%. 7%. All right, so Mr. Ko, So let's try to write out the differential equation.
Okay, so I got ds over dt equals, I'm not sure if this is right, but I think it's 100,000 plus
Okay, that's the 100,000, like it was here, is an initial condition. Initial conditions, it works in reverse in differential equations. So initial conditions are dealt with last.
Okay, I think I got it then.
That's the last thing that you would be using. So
Would it be
try again.
0.07 times s minus 8,000?
That's correct. So naturally, the money is going to grow at a 7% compounded continuously. So that's what this does. This is like your natural population growth. But then artificially, you're going to be taking away money so you don't have too much of a balance so that you eventually pay off your mortgage. So you're going to be subtracting $8,000 a year continuously over a year, but 8,000 a year. And that would be your differential equation. Rate in minus rate out, just like the mixing problem. Very similar to the mixing problem. Okay, and then initial condition, S of
S of 0 equals 100,000.
That's correct. That's correct. All right, so why don't we quickly try to solve it, Mr. Cole?
So you would do what's it called? Integrating factor for this one.
Yeah. So what would be the next step?
So you would move the 0.07s to the left side.
That's correct. Keep the negative 8,000 on the right. Okay, and then next, what's
then
U equal to?
U is equal to e to the integration of negative 0.7 to the dt.
That's right. All right, we've solved these so many times already. Let me just skip ahead because we've solved this many times. So just skipping some of the details, they're in the notes. So S is equal to 114,286 plus C e to the 0.07t. All right, so we know how to solve these with the integrating factor technique. And they're in the notes once again if you need help, right over here. Okay, so how do we find C?
So to find C, you would plug in your initial value. So you have S is, so T would be equal to 0 in this case, and S would be 100,000.
That's right. So when you do that, you get S is equal to 114,286 minus 142,286. So 114,286, 142,286. No, sorry, 14,286. I copied it wrong. 14,286 e to the 0.07t. Okay, so the question is, when will we pay off our mortgage? So you want to know when we will pay it off. At $8,000 a year, just set it equal to 0. So we would set this equal to 0 and figure out when we finally paid off our mortgage. It looks to be about 30 years, 29.7 years.
Sir, I have a question.
Yeah,
Where did the 14,286 come from again?
So what you would do is you would plug in T
Oh, okay, yeah.
Zero.
Okay, just making
S
sure.
equals 100,000. So it takes you 29.7 years to pay off your mortgage. And if you want to know how much are you paying in total, well, you're paying $8,000 a year for 29.7 years. So you end up paying back $237,648. So this is natural with a 7% interest rate. And when the rate gets lower, it will be dramatically less. Right now, if you have good credit, you can get like a 2% or 2 to 3% 30-year mortgage, which is, never happened in the last, 1,000 years probably. So it's a good time to buy a house. Okay, so here's your principal going down to zero at 29.7 years. At the very beginning of a mortgage, you're mostly paying interest because the compounding is so powerful. But eventually, your payment catches up and it sharply will bring down your balance. All right, any questions so far? I think this concludes part 1 of our course, which is the first order differential equations. And we're going to jump to second order in a moment. Okay, one of the applications we're going to look at is electrical circuits. And I know you'll take a course in electrical circuits at some point. So here we have a voltage source, E of t, that's energy. We have an inductor, L, R, a resistor. So L is the inductance, R is the resistance, and I is the current. It measures how many electrons are essentially flowing through your wire at any given time. And from physics, you get a nice Kirchhoff's law, you get a nice differential equation that measures the voltage drop over each component. So L di dt, the rate of change of the current, times inductance, plus resistance times the current is equal to the voltage that's being produced. So that's an LR circuit. And that can be solved with first order differential equation. RC circuit, resistance, capacitor. So Q is the charge on the capacitor. I is the derivative of the current function of the charge with respect to time. So if you measured the charge on the capacitor at any given time and took its derivative, that would be the current. So Ri, resistance times current, plus 1 over capacitance times Q, the charge function, is equal to the voltage that's being produced. Now, this is an equation with I and Q. Doesn't look like a differential equation, but you can write I as dq dt, and then you can write it as a first order differential equation. So an RC circuit can also be solved with a first order differential linear equation. So they're both, you might see these in the homework. Finally, LRC. Well, what if we have all 3 components at the same time? So if we have an LRC circuit, well, it turns out you need a second order differential equation to handle that. No derivatives there, just a piece of dried marker or something. All right, so LQ double prime, that's the charge on the capacitor, plus RQ prime, plus 1 over CQ is the voltage function. And once again, the current is the derivative of charge with respect to time. So we need to study second order if you want to be able to handle a circuit that has an inductor, a resistor, and a capacitor. All right, so just keep in mind these formulas. You'll need them to solve various homework problems. Basically, you'll be given the values L, R, and C, and then you can find things like the current and the charge. Okay, so we'll come back to that in some real problems. All right, so now for a good amount of the course, we're going to be studying second order differential equations. They're a lot more important than first order. They're used a lot more in engineering and physics. So in our course, we're going to stay with a rather simple case, which is second order linear differential equations with constant coefficients. So that means we're not going to have functions in front of these y's. They're just going to be constants. So for example, 2y double prime plus 3y prime minus y equals 0, y double prime equals y, which is y double prime minus y is 0, and y double prime plus y equals 0. Okay, so notice that we're not allowing multiple functions to multiply our y's. However, as you'll see in a moment, we are going to allow functions on the right-hand side that do not multiply the y's. We have the independent variable, here is x, y is the dependent variable. Here t is the independent variable, y is the independent variable. Sometimes we'll have x as a function of time. T will be independent, x will be dependent. So just be careful. Okay, homogeneous. So a few terms we're going to have to learn. Homogeneous means that when you move all the y terms to the left side, you're left with zeros on the right side. So these are homogeneous. Here are these three examples. These are not homogeneous. There's an x squared plus 1 here and a sine of t there. All right, so that'll make an important distinction later on when we go to solve them, whether it's homogeneous or not homogeneous. It'll
Wait,
turn
sir,
out,
could you,
yes.
you cut out that for that last
No.
like 20 seconds. Can you go over non-homogeneous one more time?
Yeah, sure. Okay, so homogeneous means when you move all the y terms to the left side, you're left with 0. Non-homogeneous, when you move all the y terms to the left, or you're left with functions that are not 0. So these are two examples of not homogeneous, and these are homogeneous. This is actually, in addition, an initial value problem. It's a non-homogeneous with initial conditions. Notice that now we have two initial conditions, because second order differential equations go along with two initial conditions in order to solve for both constants that will come about. All right, so you understand now? Homogeneous, not homogeneous? You able to hear?
Yes, sir. Thank you.
Okay. All right. First principle we need is called the principle of superposition. So if y1 and y2 are solutions of 1, so this is equation 1 here, then so is linear combinations. So if you take the second derivative, the first derivative, the original function, and you just plug this in to this, assuming that y1 and y2 both independently solve the differential equation, then you'll see that the linear combination of the solutions, this is called a linear combination, c1y1 plus c2y2, is also a solution. This is where the word linear comes from. When differential equations are linear, you're allowed to add, subtract, and linearly combine two solutions to get a new solution. All right, so that's easily seen. So let me just give you a little example. So let's say, so for example, y double prime minus y equals 0. Maybe you guys could check this out. I'll slow down a little bit. So let y1 equal e to the x, y2 equals e to the minus x. Verify 2y1 plus 3y2 is also a solution. So let's very quickly work this out. So everybody take a few minutes, see if you could show that this is a solution given these two are solutions. All right, Mr. Lynch. So why don't you give it a try? So what do we have to do here? Let's call this y.
So
Call that y there, okay. All right, so what's y prime equal to?
so we're taking. Okay.
So y would
I started doing something else. So
all right, so y would be 2e to the x plus 3e to the minus x. What's y
yes.
prime equal to? 2e to the x
Plus,
plus,
actually, wouldn't it be minus 3 to the
that's right.
3 to the negative x?
Okay, and y double prime?
Would be the same as original y
That's right.
plus 3.
The double negatives would combine. Okay. Okay, so now you could easily see y double prime minus y must be 0 because that's the same thing as saying y double prime is equal to y. So it clearly satisfies the differential equation. And the reason it works is because when you take derivatives, constants just fall through the derivative process, and so do plus and minus signs. So it's no surprise that we have the principle of superposition. Okay, very good. Any questions so far? All right, so how did I just come up with these solutions here? Well, take a look. So I basically started with a guess. So y double prime minus y equals 0. Let's guess that the solution is e to the rx. You know, why did we guess that? Well, we know the derivative of the exponential is itself, and we know the derivative of e to the rx is basically a constant times itself. It's worth a try to plug it in. We'll see soon that this is part of a general method. So it's not going to be really a guessing type of class, as you'll see. So, all right, but either way, let's just guess e to the rx. So we plug it in. And if you plug it in, we compute. So if y equals e to the rx, y prime is r e to the rx, and y double prime equals r squared e to the rx. Okay, now plug y double prime and y back into the differential equation. So we would get r squared e to the rx minus e to the rx must always be 0. Factor out the e to the rx, and we get r squared minus 1 is always 0 for all values of x. Well, this term here is never 0. So that means r squared minus 1 must be 0, which means r is plus or minus 1. So plugging back r into e to the rx, you get e to the x and e to the minus x. We get two solutions to the differential equation. To get, now this is very important, so to get the general solution, you take the linear combination of your two independent solutions. See, e to the x and e to the minus x are called linearly independent. They're different solutions, but they're also of a different, they're not related. You know, so what do I mean by being related or not related solutions? So this is a little bit of a subtle matter, so let me try to explain. So we can say that, you know, e to the x is a solution. And then we could say 2e to the x is a solution. But they're too similar to each other. They're only they're only constant multiples of each other. So we would say that e to the x and 2e to the x are not linearly independent. Right? So that's what, that would be the conclusion. That would be the definition. These are not linearly independent. They're too closely related. You can get one by multiplying the other by a constant. However, e to the x and e to the minus x are independent. No matter what you multiply one of them by, you'll never get that one. They just, look at their graph. E to the x goes up like this. E to the minus x goes down like this. And you could flip this one over. It would look like this. You could rescale it. It would look like this. But you'll never get this picture from these pictures. They're too different. So that's what we need when we solve a second order differential equation. We need two independent solutions. And equation 2 here, the general solution, this gives all possible solutions. All right, so we just had a whole page of definitions and stuff, so make sure you review this page at some point. It has the important concepts. Once we get these concepts down, then we could start solving problems. So any questions on the definitions and some of these concepts? Okay, so let's see how to actually solve second order linear differential equations with constant coefficients in the homogeneous case. I know that's a mouthful. I'll say it again a little slower. Well, it's right here. So second order linear differential equation with constant coefficients in the homogeneous case. The good news is our differential equation class is rather simple, and we will only really focus on these two cases for much of the rest of the course, homogeneous and non-homogeneous. We're not going to have complicated functions in front, though you definitely can, and they're definitely important in real life. But our classes, we just don't have enough time to do everything. However, I don't know, this is not really good news, but if you end up failing this course, the new curriculum has been totally changed, and the new differential equations class will be on steroids. We'll cover a lot more stuff. So that's good motivation not to fail, because the next time this course is offered, it will be with the new curriculum and it'll cover a lot more stuff. Okay. So there's going to be three cases in solving the second order linear with constant coefficients. And the first case is corresponding to the quadratic equation when you have two real distinct roots. So let's go through this and see, how does this differential equation lead to this algebraic equation? Well, let me see if one of you guys could help me with this one. Mr. Pla. So any suggestions? See if you understand some of the things we've been doing. How could we go from this equation here, this differential equation, to this algebraic equation, which is called the characteristic or auxiliary equation? All right, something to do with guessing y equals e to the rx. So let's try, everybody take a minute. I'll come back to you, Mr. Plana, in a minute. Take this possible solution, plug it into the general differential equation right here, and see if you can derive the characteristic equation. Okay, so Mr. Plus, so what do we have to do here? So y
So
prime is,
y prime is r e to the rx.
okay, that's right. Y double
Y
prime,
double prime is r squared e to the rx.
okay,
And then you can plug that back in and get a r squared e to the rx plus b r e to the rx plus c e to the rx is equal to 0. And then you can factor out the e to the rx. You get left with that that equation you have on the other sheet.
that's right. So notice this is an equation of functions. It's not a algebraic equation that we're just solving for a particular value of x. This is true for all x. No matter what x you plug in, you'll get 0. So that implies rather quickly, since the exponential is not 0, never 0 even, but as long as it's not always 0, this is a constant, will always have to be 0. So you're not going to want to, so you won't do this yourself. Some students do. I notice on their test, they do this for every single problem. Don't do. You're going to go directly from here to here. Now we're just showing you why, so we don't have to do it every time. So AR squared plus BR plus C is 0. And this is just a regular quadratic equation, right? So we know how to solve the quadratic equation. If you have the TI-36X Pro, it's built into it already. If you don't, memorize the quadratic equation. And negative b plus or minus the square root of b squared minus 4ac over 2a. Make sure you have a, b, c set up in this way, with the highest power with a. And case 1 is R1 and R2 are real and distinct. So once you find R1 and R2, your two roots, you form the general solution like this, by taking a linear combination of the first solution and the second solution. All right, so everybody, this will take you a good 5 minutes probably. See if you can solve this differential equation. This is important because it's going to lead up into many other problems. We're going to be doing these kind of equations for a while. So make sure you learn this fast and good. Any questions so far? All right, so let's get it started. Miss Raya. So what's our first step?
Where we have to like solve for like y prime and y double prime.
Well, we want to go directly to the characteristic equation. And then we want to solve that equation. So what's the characteristic equation?
It's y double prime minus 5y prime plus
This is the
6y.
characteristic equation.
Oh, the AR squared
Yeah.
plus BR equals plus C equals 0.
Yeah, so what will it be? So A, what's A equal to?
A is 1.
Okay, so the characteristic equation will be r squared minus,
Minus 5r
okay, plus
plus 6
equals,
equals 0.
all right? So solving for r,
So it would be r equals 5 plus or minus
so
the
r
square root.
minus 3. You could either use the quadratic equation, right? Or you could just factor this one. It factors pretty easily, so. If you can factor, you might as well try factoring first before using quadratic equation. Right? So r is equal.
Yeah. So r would be equal to 3 and negative 2,
Try again, 3
or
and
3 and 2.
positive 2, right?
Yeah.
Okay, so let's form the general solution. So let's write down the general solution. All right, so what's the general solution? C1 e to the,
E r1x
what's R1?
3
So e to the 3, C1 e to the 3x plus C2.
e to the 2x.
Okay. All right, I'll give everybody another minute to now plug in the initial conditions and see if you can solve for C1 and C2. Any questions so far?
Sir,
I
does it matter for the R values? Does it matter if, like, say, for R1 you put 2 instead of 3?
No, it doesn't matter. In the end, you'll get the same specific solution. It may look different over here at this step, but at the very end, with initial conditions, it'll be the same final answer. Yeah, it makes no difference. It's just an arbitrary pairing. Okay, was there another question? I thought I saw a second question. Anyone else have a question? All right, so take a minute or two to solve for C Okay. Mr. Stanley, so let's give it a try. So let's try to solve for C1 and C2.
All right. So starting off, what I did was I started for y is 0 equals -1, which got me C1 plus C2 equals -1 because e to the 0 is just 1. And so,
That's correct. Good.
yep. And then for y prime is 0 equals 5, I pretty much did 3C1 e to the 0. So it could just be 3C1 plus 5C2 e to the 0, which is
Right,
just,
so we're working out the first derivative, right?
yeah.
Calculate the first derivative first. So let's do that.
Yeah, I was jumping steps a little bit. So that's the first derivative. And then pretty much I just plugged in 0 and set it equal to 5.
Okay, good. Be careful with this step, in case you have minus signs and stuff. So make sure you calculate out the first derivative fully and then plug in x equals 0. So we would get 3C1 plus 2C2. All right, so for this one, you could definitely solve it by hand, but I recommend we're going to do a lot of solving things by hand later in the course. And at this point, you might want to just learn to use your calculator to do this. We will learn how to do it properly, as I said later. So you go to System Solve, 2x2 linear system. Okay, C1 is X and C2 is Y. So we have a 1, 1, and the right-hand side is a -1. And we have a 3, 2, and 5. All right, so I plugged in the system. You'll notice in many, many courses, you're going to be solving systems of equations. So you might as well learn how to do it on a calculator. All right, so C1 plus C2 equals -1. 3C1 plus 2C2 equals 5. Looks good. Solve. So I got 7 and -8. So C1 is 7. C2 is -8. All right, and so what do we do with these values, Mr. Stanley?
You plug them back into your original diffie-q or your original
Into the
derived equation.
Into the general solution, right?
Yeah, that's what I meant. I apologize.
It's all right. These are new terms. There's a lot of new vocabulary that we all have to learn. It takes a little while to get them. Okay, so the specific solution to the initial value problem, basically our final answer, as you would say, but it's the specific solution to the initial value problem would be 7e to the 3x minus 8e to the 2x. Make sure you put the right C1 and C2 back with your choice. Otherwise, you might have a mix-up here. So this is why we'll all get the same answer in the end, as long as we're consistent. Okay, so it looks like we're exactly almost out of time. Maybe any final questions about what we did so far? Starting
You're
second.
gonna send the notes out by email again, sir?
What have I sent you so far? What do you have up to?
I think we have up to the gravitational with -b, like when it's up, and then the
Oh, okay. The falling body
air resistance.
air resistance problems. Okay. All right. I'll try to send that out by tonight. Okay. Yeah, I'll send out the new notes tonight. I'll turn them into a PDF file.
Also, sir, is there any way we can get our tests back by email or something?
Well, it'll take me too long to scan each one and email each one. So my system is, your office hours are tomorrow, Tuesday, second period. So if you're concerned about your test or you really want to see it, come to the office hour and I'll show you, while you're the only one in the Zoom, I'll show you your test on my camera. But then I will give you the test back at our next exam. You'll have the hard copy back when I come in next to give the exam. But if you want to see it sooner, then come to office hours and I'll project it for you. Okay.
All right, thank you.
Sure. All right, so take care, everybody. And I'll see you all tomorrow.
Thank you,
Sir.
sir.
Yes, sir.
See you tomorrow, sir.
Thanks, sir.
Welcome.
Sir, I have just one question regarding the calculator.
Yeah.
You can stop recording if you'd like.
All right, hold on.
Yes, sir.
Stop recording.